So, on to the main programme, and it's my pleasure to introduce Michal Michalowski. It's so rare that the speaker actually provides you with absolutely precise instructions as to how to pronounce his or her name. And Michal is going to talk about massive stars formed in atomic hydrogen reservoirs. Over to you.
Right. Thank you for introduction, and thank you for inviting me to talk here. So first of all, if you have any questions, anything is unclear, you are very welcome to interrupt me and ask during the talk. I'm Michal. I'm working at the University of Edinburgh, and this talk will be about atomic gas and massive stars. So that's the very simple plan. I will introduce the subject of gas inflow and why gas is important at all in galaxies, and then I will go to my results, which are from the H1 atomic gas survey of gamma-ray burst host galaxies. So let's start with the introduction. So that's my motivation slide, which is empty, so that's embarrassing. I have checked it 10 minutes ago, but it doesn't go off now, which, well, okay, I will tell you what is supposed to be there. No. Okay, so I have no motivation. So this beautiful motivation, which is not mine anyway, so that's not a big deal, shows how stars are being formed. We have a big gas cloud, and the cloud starts collapsing, fragmenting, and then you have in the dense pockets, you form stars. So that's what we know. What we don't know is how this gas ends up in galaxies. Because galaxies have some gas reservoirs, but these reservoirs are not big enough to sustain star formation. So my question is, how this gas, which you don't see here, ended up in galaxies? I have two animations, so maybe the second works. So that's the theoretical picture, how gas gets into galaxies. You have a galaxy, you have intergalactic medium, so you have some diffuse gas, you have some filaments, and gas is very likely, or according to simulations, certainly flowing into galaxies and fuel star formation. So provides the fuel for star formation. Unfortunately, observationally, this gas here is impossible to observe. It's so dilute that the emission is so weak that we don't see this. This is just a simulation. And obviously, when you zoom in, you see a galaxy with dense gas where star formation is occurring, and that's what we see. We see that one. We don't see this picture. So this is a bit tricky. So I think I know of 3 examples of something which resembles gas inflow onto galaxies, so some direct evidence of gas inflow which provides the fuel for star formation. And I will show you all of them. So this is one quasar. This is excited gas emission, and well, there is some filamentary structure which was interpreted as a gas inflowing onto the host galaxy of this quasar. So that's number 1. That's number 2. It's a dwarf galaxy. So the blue is the stellar emission, red is the CO, so carbon oxide, monoxide emission, so molecular gas, and you have this structure here which looks like a gas inflow into galaxy. Okay? And that's very recent, number 3. I think it was a few days ago or a few weeks ago. This is redshift 3, so it's much more difficult than the previous case. You have a galaxy which is kind of smallish, 10 to the 9 solar masses, and you have these structures here, which are real. This is not just noise. So, well, maybe gas is inflowing onto the galaxy. And that's it, about inflow of gas into galaxies. That's it. As far as I know, this is the only 3 cases when we actually see something which resembles gas inflow onto galaxies. And there are a lot of indirect evidences as well. So you have a big galaxy and a smaller one, and the contours is the H1 atomic gas emission. You see some bridge here, so probably it was a collision. This small guy went through here and like extract a bit of H1 from the big guy. But eventually the small galaxy will end up merging with that galaxy. So the gas the small guy is carrying will flow into the big guy. So that's the indirect evidence that gas inflow must happen, in this case in a form of a dwarf galaxy falling into the big guy. Whoops, I should press this one. Another indirect evidence is the existence of extraplanar atomic gas. So you have a edge on this galaxy, and the blue is the H1 emission, and you have these structures here. Some of it could be gas outflowing of this galaxy, but at least part of it, and maybe all of it, is just gas inflowing onto galaxies. So maybe, well, this is also evidence of gas inflow. Then there is some other interesting studies. This is the statistical studies of big galaxies, which were divided into two groups of H1 rich, the red ones, and blue ones, H1 poor. And then this plot shows you the average mass of companions of these galaxies as a function of distance from them. And you see that the H1 rich galaxies have also H1 rich companions compared to H1 poor galaxies. So if the central galaxy is rich in gas, the surrounding galaxies are also rich in gas. And obviously it probably goes other way around, right? That if you have rich environment, they fall into galaxies, fuel this central galaxy, and the galaxy is getting rich as well. So this is indirect evidence again of the interaction with the environment, and very likely in a form of gas inflowing onto the big guy. And then some morphological evidences of gas inflow. You have this warped extended disk, which, well, dynamically we know that it's probably because of gas cloud got into the galaxy, disturbed the morphology, and that's the result. And the same with asymmetric profiles of H1. If you have kind of asymmetric looking galaxies in H1, it's very likely that it has just accreted either a small dwarf satellite or just gas cloud, which disturbed the morphology. And then the last thing is something, well, it's not a direct evidence, well, it's not even indirect evidence of gas inflow. It's something interesting which we need to interpret. So these are metal poor galaxies, local galaxies. And the arrow shows the direction of the slit. So the spectra was taken of both of them. And now here, this line shows the H alpha emission, so star formation along the slit, so in that direction. And this shows the metallicity, like 3 different options of metallicity. And what you immediately notice is something interesting, that it has some metallicity holes in them. And these holes in metallicity, so like lower metallicity, corresponds to the position where star formation, or H alpha emission, is the highest. And this is counterintuitive, because if you have more H alpha, means more star formation, which means more massive stars, so it should be more metals, because massive stars, well, any stars, produce metals. So this is very counterintuitive. And it was interpreted as that the fact that there is large star formation is the consequence of accretion of metal poor gas from the intergalactic medium. So this galaxy was normal and flat with metallicity. It got some metal poor gas from the surrounding. It started star forming in that region where it accreted, and also that region is metal poor because the gas, which was metal poor in the surrounding, didn't have time yet to mix with the more metal rich environment. So that's very interesting. And even more interesting is that the same effect was observed at redshift 3. So this is local, these are local galaxies, but this is redshift 3. And we see similar thing. These are metallicity maps now. So high metallicity is red, blue metallicity is, blue is low metallicity. So usually you have a gradient of metallicity that center of galaxy is metal rich, and then there is a gradient towards the edges. Here it's opposite. You have low metallicity, maybe I should stand where the microphones are, low metallicity in the middle and higher metallicity at the edges. So this is very difficult to explain in any kind of galaxy evolution model, except of the model which just involved a gas cloud which just got into this galaxy and settled in the middle. And this gas cloud was metal poor, and that's why there is some kind of hole in the middle in the metallicity map, and the same for that one. All right, so that's about gas inflow. So the conclusion is we don't really know much. We need to still understand this process. And this inflowing gas is fueling star formation. So first I will tell you which kind of gas I will be talking about. So atomic gas is where two hydrogen atoms are separate. Molecular gas is where they are bound. And this structure is emitting 21 centimeter lines. So atomic gas is very easy to observe, well, relatively, up to redshift 0.2, let's say. This molecule doesn't emit any reasonable lines. So whenever I say molecular gas or molecular hydrogen, I don't mean the emission of that line. I mean the emission of carbon monoxide, which is another molecule. And, well, there is reasonable correspondence between these two. So if there is CO, it's probably some proportional amount of H2. This conversion has some problems, but that's what I based my talk on, basically. And now, which of these gas, the molecular, the atomic, or molecular, is important for star formation? Well, since many years, we know and accept the notion that it's molecular gas which is fueling star formation. So molecular gas is required for star formation. And that's one of the evidence. If you plot the density, the surface density of star formation and surface density of atomic gas, so basically you select each pixel and of a galaxy and measure how much star formation there is in this pixel and how much atomic gas there is and how much molecular gas. So molecular gas correlates perfectly with star formation rate. There is a clear trend here, whereas atomic gas is not correlated at all, or very, very weakly. So that's one of the evidences that molecular gas is required for star formation. And in terms of where these phases occur, well, in the intergalactic medium, we only have atomic hydrogen. But if you have a dense cloud, then you have a layer of H1, which is shielding the radiation from the stars. And then inner in the cloud, you have H2, the atomic molecular hydrogen, but also CO and other molecules. And, well, this plot also shows that there is a problem. If you decrease metallicity, at some point you can have molecular cloud with molecular hydrogen, but no CO, no C+. So, well, this is very difficult to observe, obviously. And the same if you decrease the size, then at some point you end up with something which is unobservable, basically, because there is no CO emission. So now I go into the introduction of gamma ray bursts, which are here. That's my second animation. I checked it like 10 minutes ago. That's amazing. Okay, so this animation shows, maybe actually this is quite nice. Yeah, this is quite a nice simulation. Maybe I will close it and, oh yeah, okay. Now it's at least shows something. Okay, yeah, so that's a gamma ray burst. That's of course not data, it's an animation. So a gamma ray burst is a massive star, like 30 solar masses, which ends its life and explodes. And then it shoots this jet, the layers of this jet collides, then the jet collides with the interstellar medium, which is shown here. And the point is that if this jet points exactly towards us, we see it as a GRB. We see first the GRB gamma ray emission, and then we see the afterglow emission at other wavelengths. So yeah, like we need to see right through along the jet to see it as a GRB. So okay, it's a massive star. So the point is, wherever we see a gamma ray burst in any galaxy, we know that there is a current star formation in that galaxy. Because if the galaxy was passive, then there wouldn't be any massive stars to explode as GRBs. So that's something quite interesting and quite useful. But there is a problem here, because there is a recent study, Hatsukader et al., which shows that these galaxies, the gamma ray burst hosts, are deficient in molecular gas. So if you plot infrared luminosity, or it's a proxy for star formation, and then CO luminosity, a proxy of molecular gas content, these are other galaxies, like low and high redshift, and these are GRB hosts. So they are offset towards lower molecular gases. And now I have a few more detections with recent APEX data, and they all lie towards the left. So GRB hosts are deficient in molecular gas. And this is something, again, weird, because I told you that GRB is an exploding massive star, so it must be connected with recent star formation. But before I told you that star formation is connected with molecular gas. So why there is no or very little molecular gas in these galaxies? Well, this is what I'm trying to explain, and I think I have find an explanation. So I will come into the survey which I conducted over the past few years, which I think provide the explanation of this problem. So the survey is H1 survey with Australia Telescope Compact Array. Only 5 targets because, well, that's the only targets in the southern hemisphere with redshift below 0.1, because if it's high redshift, then H1 observations are not feasible. And it's 150 hours on source plus calibration. So it's quite expensive program anyway. But yeah, just 5 targets. These are faint galaxies. And these are the spectra, the H1 spectra. So we detected 3 of them clearly. You have this, so this frequency or velocity as a function, flux as a function of velocity. There is a clear H1 line here, here, and here. The red curves here are just to fool you. This is not a detection. And there is another detection here, which is companion of that object. So when I plot the contours, so the image is the optical image. The blue circle is the position of a gamma ray burst, where the gamma ray burst exploded, and the contours is H1. So yeah, we detected these 2. The other one has too poor spatial resolution to show it. And then there are these 2, well, this is the host galaxy, and this is some other companion, which I will come back to later. And that's the similar plot which I showed you before with deficiency in molecular gas. So now this is atomic gas as a function of star formation. The red points are GRB hosts, and they lie exactly where they should. Maybe a bit higher, but this is speculative, given that there are 2 upper limits here. So they are exactly where they should be. So the first thing which came to my mind is, okay, if they don't have molecular gas, but they do have atomic gas, maybe star formation is fueled by atomic gas, not molecular gas. This is a bit controversial, and I will try to explain why I think it's possible. First of all, if you look at the position of the H1 emission, where the H1 emission is coming from, this is of course tricky because this is the resolution, so the resolution is comparable with the size of the galaxy, so with this data I cannot say much, but you can see that the H1 center is not where the optical center is. It's shifted, and it's shifted towards the GRB position. And the same here. The center of H1 is not here, but it's shifted towards the GRB position. So, okay. With the low resolution data, it can be, this is not astrometry. I've checked it very carefully. This is not the astrometry shift. It's real offset. So with so low resolution data, the reason for that could be that there is more H1 in this position and in this position, and then that's why the centroid is shifted towards the GRB position. And that's exactly what was later observed for one of these guys. This is high resolution H1 observation, the same galaxy. And yeah, H1, the highest peak of H1 concentrate exactly where the GRB exploded, shown by this blue line here. So this confirmed my my notion that there is a lot of H1 at the position of the GRB, which means that maybe this H1 is fueling star formation. And now also there is another evidence, this object. This is HST image, quite deep. There is really nothing here. These are stars. These are galaxies at different redshifts, so they cannot be counterparts. There is really nothing here. So, well, it's a starless atomic gas cloud or very low surface brightness object. So, well, I could say that this is a gas cloud which is just inflowing onto this galaxy. So I have just caught gas inflowing into onto the galaxy. That's pretty cool. Of course, I will need high resolution data to confirm that, but it looks like that. So now, so I tell you, okay, maybe the star formation in these galaxies is fueled by atomic gas, which is against what we know, because everybody would tell you that it's molecular gas which fuels star formation. So I need some theoretical backup for that. And this is shown here. So this is the simulation of a gas cloud, which is initially hot and atomic, and then it's led to evolve at different metallicities. So the black curves are the temperature starting very high and then cooling off. Of course, if it's higher metallicity, it cools faster, lower metallicity cools slower. And the blue curves is the molecular gas fraction. So it starts fully atomic, and it ends at some point with 1, so it's fully molecular. And the time unit is in freefall time, so star formation occurs somewhere between 1 and 10 freefall times, or 1 and 3, or well, somewhere here, as long as the temperature is low enough. Because if the temperature is high, then there is no star formation, because then the gas cloud cannot collapse. So if you have a solar metallicity cloud, it cools very quickly, then it evolves. At some point, at this point, star formation kicks in, but at this point, the gas is almost fully molecular. So that's what we know. The star formation occurs in molecular gas. That's all fine. But if the metallicity is lower, and not crazy low, but kind of half solar or third solar, then the gas cools very quickly anyway, a bit slower, but not that slow. So it is cold when star formation can occur, but the molecular gas fraction is very low. Like if you say, okay, 10% solar, so -1, when star formation starts, it's almost entirely atomic. Maybe 10% of it is molecular. But it's cool. It's well, it can collapse. There is no reason for star formation not to occur, right? Like if you don't invoke any physical mechanism that H1 is really required from physical reasons, this cloud, which is atomic, can just proceed with star formation. Of course, at later stages, this cloud will get molecular, so later stages of star formation will go in the molecular phase in a usual picture. But at the very beginning of star formation, this star formation is occurring in atomic phase. And that's what I think happens for GRB hosts. They have just accreted atomic gas, while one of these clouds is still seen, as I interpret it. And they are exactly here. The GRB explosion is a signal of very recent star formation, so it all fits in. The point that there is no much molecular gas is because it has not have time to convert H1 into H2, and star formation is occurring in atomic phase. And to show you some little backup for that theory, this is again the metallicity map, but of GRB host galaxies. So the same story, the blue is low metallicity, red is high metallicity. GRB occurred in this point and this point, and you see it's always very close to metal poor regions. So again, it fits the picture that some metal poor gas from the intergalactic medium just got into this place, start forming stars, and that's why we see star formation there, that's why we see atomic gas concentration there, and that's why we see low metallicity there. And the low metallicity for GRB positions is very common. Like if you plot metallicity at the GRB position against the metallicity of average over the host, the metallicity at the GRB position is always lower than the average metallicity. So this is something normal and usual. It's in every case. So I finish here with the conclusions. So the inflow of gas in general is required for almost any galaxy. This is not, we cannot just see it, but it's there. It's for sure there. And it's just difficult to detect. And GRBs, I claim, they are at the very beginning of star formation when they just got the atomic gas accretion coming into them, and star formation is occurring in this atomic gas phase, and obviously later it will convert into molecular phase. And this result, if confirmed, will show that the connection between star formation and atomic gas is stronger than previously thought or assumed. More details are in this paper, and as I told you before, the next step for this is obvious high-resolution H1 observation, because then I will see the morphology, dynamics of this system, and then I will be able to tell you more about this. Thank you very much.
Before I take questions, I should just remember to announce at the beginning that Michal is the RAS Winton Capital Award for Astronomy for this year, or for last year now. So, any questions? Oh.
Don't worry about that. You need it. All right, I'll talk into this.
It's so we can play you forever and a day.
You've said something that's very important for high mass stars. Do you think that it really holds for low mass stars, or do low mass stars only occur somewhat later? And the last thing you said was that this is high mass stars but of low metallicity, and most stars do not have low metallicity.
All right. So first, whether it applies to low and high mass stars, I think it applies to everything, because the stars are born. Well, if there is a star formation episode, the high mass stars are born, and some of them explode as GRBs, and low mass stars are also formed. So this is the same process.
For these stars?
For this, well, okay, I don't see it here, but like from the theory of star formation, I think apart from extreme low metallicities, crazy pop-3 stars, the range of masses of stars which are being formed is always very broad. It's not that you form just high mass stars or just low mass stars, as far as I understand. But I cannot see that in this data, of course. And the second, the metallicity, yeah, GRBs, well, are very useful, but it's very likely that they are not the representative population of stars. Maybe they trace only the low metallicity stars at given epoch. That's perfectly plausible. So there are theoretical models which predict that high metallicity star would not explode as a GRB, because then the cooling is loss of the angular momentum is too high, and it cannot drive the jet. So it's very likely. It's less of a problem at high redshift, because at high redshift the low metallicity is a normal metallicity, so then every star would be well, kind of similar to GRB population. But at low redshift, of course, they may not be, or they are probably not representative.
Yeah, I mean, I find your explanation really appealing, and you probably know, it mirrors a debate that's been going on for a long time, trying to understand star formation in low metallicity galaxies in our own neighborhood, where you see the same thing, very little molecular gas, but very high rates of star formation. But in that debate, the reason it's still a debate is the other possible explanation is, as you showed in an earlier slide, is that molecular gas is there, but you're not seeing it in CO. So what is the argument against that as a preferred explanation?
Well, the metallicity of these galaxies is not that low. It's well, on average, I think it's on average over entire galaxy is 0.5 solar. So at that metallicity, we should still see CO. It's not like 10% or less than that. So I think this is not a problem. And actually, the plot I showed you, the metallicity, yeah, that one. These two galaxies are solar metallicity. So, wow, you can invoke some special physical properties, but as we know, they should show a lot more CO emission. These two are normal metallicity galaxies.
Thank you. Yes. Would it be the case that even starting from a cloud of atomic hydrogen, and from beginning to end of process, you're going from atomic hydrogen to plasma in the fully formed star, so certainly not molecular hydrogen there, would there be an intermediate stage where the collapsing cloud becomes sufficiently dense before it gets hot that it would go molecular?
Oh yes.
Or does gravitational heating stop that happening even at that stage?
I think that's the generally accepted picture, that this H1, so atomic cloud, is getting molecular because of the shielding.
Yeah.
And I don't want to overturn this theory.
No.
It's just I think that at the very beginning of star formation, it's possible that gas starts star forming before it gets molecular.
Yes.
But it's definitely, the molecular phase is definitely there. We see
Well,
that.
why I asked that question was because I was going to ask, is there likely to be any difference between stars, the final product, produced from atomic hydrogen clouds and from molecular hydrogen clouds? If, of course, it goes through an intermediate molecular stage,
Yeah.
maybe the slate's wiped clean and that
I
can't
doubt.
leave a...
I doubt, because this is still, okay, if the process of star formation is somewhat different, maybe, I don't know much about chemistry, maybe the cooling is different, or then maybe something, but in general, well, when you form a star, this is not a molecular gas star or atomic gas star, it's like, it's just hydrogen star, so I wouldn't suspect that, but maybe if there is some physical, like maybe H1 gas would cool faster and make it fragmented faster, so maybe the initial mass function is different but this is very tricky. I don't think we are there yet, in either with observations or with theory.
Okay, well, thank you. We need to move on now.